everyone. We just had a very nice ITC discussion. I wanted to advertise it again because not everyone is aware of it. The ITC colloquium was transformed into a discussion forum in which everyone is welcome to learn about some questions that are not resolved. The idea is to foster interactions and collaboration. So you're all welcome at 11 a.m. every Thursday. And as usual, we have the ITC lunch. This time, thanks to a generous donation from Eric Ito sitting next to me here. And so today we have 4 speakers, as usual. Cassi Lochhaas, who just joined us, will speak first. She's a new Hubble and ITC fellow, and she will tell us about the non-equilibrium circumgalactic medium in the FOGGIE simulations. Then we'll hear from Mike Foley. Where is he? Somewhere. No. Over there. From here, and he will tell us about shock turbulence interactions in star formation. And then we'll hear from Eric Ito, who will tell us about fragmentation of molecular clouds by entropy fluctuations. And finally, from Misha Rashkovetsky. Misha is over there. Student here, and he will tell us about the semi-analytic covariance matrices for 2-point correlation function of DESI galaxies. Cassi, go ahead.
All right, thank you so much. Hi, everyone. As Alvi just mentioned, I'm a new Hubble Fellow here. I'm technically at SAO, but I'm also affiliated with the ITC. So because I'm sort of brand new here, what I'm going to be telling you about today is actually some of the work that I did as a postdoc at Space Telescope Science Institute, which was my previous position. So I've been doing this work with my collaborators that I've listed on the screen here, primarily Molly Peoples and Jason Tumlinson. And I've been mostly working on the FOGGIE simulations, which is one of these simulations that we're actually watching right here. So what I'm most interested in is sort of the circumgalactic medium. And in case you have never heard that phrase before, the circumgalactic medium is really sort of the conduit between galaxies and the entire rest of the universe. It's usually defined as sort of outside of the ISM and disk stars of a galaxy, but still within the virial radius, or roughly. It is multi-phase, and when this movie restarts, we can see that very easily, meaning there's a lot of density and temperature structures there. It's also multi-structured, meaning there's a lot of small-scale structure, large-scale structure, and it's very dynamic as well, which is very clearly exhibited by watching these types of simulation movies. Unfortunately, it is also very diffuse and difficult to observe. And usually the way that we observe the CGM of a distant galaxy is to look for a background light source and then look for absorption in the spectrum towards that source as its light travels through the CGM of some foreground galaxy. So the types of questions that I'm interested in trying to solve are, what is the role of a galaxy's surroundings, this CGM, in its evolution? And how do we develop physically and also intuitive models for galaxies and the CGM and their connection, and of course connect that to observations, much like this type of observation here. To sort of take a step back and look at a slightly simpler picture of the circumgalactic medium, this really nice cartoon from a 2017 review lays out the different components that we might expect to find there. There's the central galaxy disk. Perhaps we have some accreting gas sort of spiraling in. We could have biconical outflows coming out from that central galaxy. Maybe some of that is recycling, falling back onto that galaxy. And sort of between everything else is also this diffuse gas component. So if we have this sort of complicated multi-component structure for the CGM, but most of our observations of it are only this sort of one-dimensional line of sight through any given galaxy CGM, you can understand that if we really want to understand the observations, we need some sort of model. We need some way to interpret this 1D information. So what I do is I use simulations that can include lots of relevant and also nonlinear physics to develop these types of models. So the simulations that I use are FOGGIE, that stands for Figuring Out Gas and Galaxies in ENSO, where ENSO is the name of the code being used. So these are cosmological zoom-in simulations where we focus on 6 roughly Milky Way mass galaxies. So much like other cosmological zoom-ins, we just pick these 6 galaxies and resimulate them at higher resolution. But the special thing about FOGGIE that other cosmological zoom-ins don't do is that we have a box that is 200 co-moving kiloparsecs on a side. And everywhere within that box, the simulation resolution, the spatial resolution, is 1 kiloparsec or better. So that allows us to pick up a lot of structure even far outside of the galaxies in the CGM in both the density and the temperature as well. We've had a number of papers so far. I've listed all of them up here, and we have several more that are coming out very soon, so keep an eye out for those. So for the rest of this, I just want to focus on one snapshot of one galaxy, although I'll mention that all the results that I'm showing here are applicable to the other simulated foggy galaxies. So we're looking at our galaxy edge-on, little box around the disk here, and then the color coding is showing us the temperature. So we can see that we have these different regions within the CGM. We have a hot outflow, which for this particular slice, because it's just a 2D slice, it's sort of just one-sided here rather than a biconical outflow. We also have these cool inflows or filamentary structures that are flowing in towards the galaxy. And then in between those flows is that warm halo gas that shows up in green on this plot. And I want to make the point that this warm halo gas is actually not static. Just because it's not participating in any bulk flows doesn't mean there's not interesting dynamics there. And we can see this if we look at the radial velocity. So this is velocity relative to that central galaxy, where again, we can very easily see this very fast outflow moving away from the galaxy, inflows coming onto the galaxy. But even up here, where there aren't really any bulk flows, there's still some interesting structure. And we can drill down into that a little bit more by looking at the velocity dispersion. So this is kind of a quick and dirty tracer for the turbulence in the gas. We can see that it's very strong within the outflow, not very strong within the inflow, but we have a good amount of turbulence in the CGM, even outside of these bulk flows. And this turbulent dynamics can provide a significant amount of energy, kinetic energy into the system, and also pressure support for the gas in the CGM. And these things are not always accounted for in models of the circumgalactic medium. So for example, my most recent paper asked this question: what supports the CGM gas against the inward pull of gravity? Usually the answer to this is, well, maybe it's in hydrostatic equilibrium, where we have thermal pressure that is providing an outward supporting force to keep that gas from falling onto the galaxy. So this slice here, this is actually the exact same slice of the same galaxy, but it's getting a little bit more abstract. So we still have this box around our edge-on galaxy disk here. And everywhere that you see blue in this slice shows us where the thermal pressure is contributing to hold that gas up against gravity. So it is sort of spread everywhere. But there's more than just the thermal pressure. We can include a turbulent pressure. In green here, we can see that's very strong, very close to the galaxy, and also within that outflow, if you remember, it was sort of coming down this way. And we can also include a rotational support as well in pink. And we see that this is sort of spread throughout a large chunk of the space surrounding the galaxy. So the conclusion here is that the hydrostatic equilibrium, just the thermal pressure, is actually not enough to hold up that gas against gravity. We need these other dynamic forces like turbulence and rotation in order to provide that supporting force. So if we're now thinking about how does fresh gas flow from the intergalactic medium through the circumgalactic medium and get to the actual galaxy to provide star formation and growth, it has to push through this very dynamic CGM. So this is what I'm working on now. This is extremely preliminary work where I'm now looking into the inflows in the foggy simulations. So this rendering shows, again, one of the foggy galaxies. This is just one snapshot in time in the center here. And what's being rendered is only the inflowing gas. We don't see any of the outflows. We don't see the diffuse gas. This is only the gas that is inflowing. And we can tell that it forms these sort of coherent filamentary structures. They are connected all the way back out to the cosmic web. They form these sort of very large, broad, coherent streams. They're falling inward at roughly the free fall velocity. They start out fairly cool. They're color-coded again by their temperature here. They start out around 10 to the 4 or 10 to the 5 and then warm up a little bit as they get in towards the central galaxy. But you'll notice that a lot of them don't actually connect smoothly all the way onto the galaxy disk. Certainly these ones up here do not connect at all. This one almost makes it, but then doesn't seem to, and there's really only one of these filaments that can actually connect onto the disk. And we can see this very clearly if we take an all-sky map of the inflowing gas. So this is a movie here. When I play it, we're going to start stepping inward in radius, closer and closer to the galaxy. But what we're looking at here is, again, only the inflowing gas. That's the only thing being rendered here, and again, color-coded by its temperature. So what we can see is we start stepping inward in radius here, is that we have these sort of cool cores to these filaments that are surrounded by a slightly warmer sheath, that green color. And this could be indicative of a turbulent radiative mixing layer on the edges of these filamentary structures. But as we get close to the galaxy, you'll notice that these filaments are starting to break apart and dissipate. You don't really see that cool core and sheath structure. The accretion is just sort of spread across the whole sky and has a lot of different temperatures to it. So what I'm currently in the process of trying to figure out is why this happens. Maybe there's some heating or mixing that's occurring. Maybe there's all that turbulence in the CGM that's just causing these filaments to be shredded before they can make it to the galaxy. Or maybe they're just being blown away by outflows. So in the meantime, I can tell you some of the properties of this accreting gas. So these are all going to be radial profile plots. The galaxy itself is down here at 0. The cores of the filaments are in purple, the sheaths of the filament in green, and then all the rest of the CGM is this orange dashed line. So everything that's not accreting. So if we look at temperature, we can see that the cores are cooler than the sheaths surrounding them. And they also heat up a little bit as we move towards the galaxy from right to left. If we look at metallicity, we can see that the filaments are very metal poor, but the sheath surrounding the filament is a little bit more metal enriched. That could be indicative of some mixing occurring on that edge of the filament. If we look at the covering fraction on the sky, so this is again pretending we're sitting in that central simulated galaxy and just looking out at the sky, the cores of these filaments only occupy about 10% of the entire sky, whereas the sheath surrounding them is quite a bit more. And finally, if we look at their radial velocity, again, relative to that central galaxy, the cores of the filaments are moving much faster compared to the free fall velocities, this black dashed line down here, whereas the sheaths are sort of slowing down throughout the CGM. So to sort of summarize all of that, these cores are cool, metal poor, fast, and small or thin on the sky, whereas the sheaths surrounding them are a little bit warmer, and a little bit more metal enriched, and a little bit slower and wider. And this is exactly what we would expect for a turbulent mixing layer on the edges of these filaments. So we have that these fresh gas inflows coming from the IGM has to push through this dynamic CGM and are dissipated along the way. And so you might wonder, how does the gas actually make it to the galaxy disk? Well, I don't have an answer just yet. This is what I'm planning on looking into next, so stay tuned to hear more about that in the future. So just to sort of finish up, I'll say that hopefully I've convinced you that the CGM is fairly dynamic. There's a lot of turbulence in that gas there that can actually keep it from being in hydrostatic equilibrium, as evidenced by the velocity dispersion. And the fresh gas inflows that fuel this galaxy have to push through this dynamic CGM, and that can have consequences for those flows. I'll leave it there. Thank you. Yes.
The density is higher at higher redshift.
Absolutely.
But one thing you didn't mention, I mean, you talked about the gas, but what about mergers with subhalos bringing gas or exciting the turbulence?
Yes, all of that is included in the simulation. So everything I showed was just one snapshot right at redshift 0, where these galaxies were selected in the simulation to not have a lot of mergers below redshift 2. So we try to eliminate that a little bit. But yes, there's absolutely going to be large differences at high redshift, and that's one of the things that I'm planning on looking into that I haven't gotten around to yet.
We have lots of questions, so we'll start with Doug and then go around.
I was a little surprised by the half-dex metallicity difference between the sheath and the core.
Mm-hmm.
Is that just because the sheath is also involving the gas that it's kind of ramming into, or what do you think?
Yes, yeah. So I think what's happening is that the filaments that are coming in should be fairly pristine, but then as they begin sort of mixing, there should be some hydrodynamic instabilities sort of on the edges of these streams that can mix in some of the higher metallicity gas in the CGM, and that ends up producing sort of an intermediate metallicity in the sheath.
Okay.
Go ahead,
So, observationally in the Milky Way, I think it's clear that some of the high-velocity cloud gas is quite a bit cooler than in your simulation. So I was wondering about that.
Yeah, so I should say that most of the things that I talked about here are probably not going to be observed as high-velocity clouds. These filamentary structures are actually fairly diffuse, whereas the HVCs tend to be a little bit more compact and perhaps a little bit higher density as well. So I'm not sure that this is sort of a direct analog to the HVCs. I will say that we do have small sort of cloud clumps in the CGM, especially at slightly higher redshift, that could be HVC analogs, but I haven't looked into that too closely.
Jesse?
Hey, thanks for the great talk. I was just wondering, for this particular galaxy, if you play it back in time, does it never touch the galactic center, or does it come in and then go back out?
For the filaments,
For
you
the
mean?
pull filaments, yeah.
That's a good question. I haven't had a chance yet to look at the redshift evolution of these filaments, but I expect that at higher redshift, the filaments should connect all the way onto the disk.
I was a similar question that I suspect you won't be able to answer quite yet. But the structures you've shown here seem very like sheets almost, rather
Yes.
than kind of the cylindrical like things
That's right.
you might imagine of filaments. And my question was going to be, have you looked at higher redshift? Are they more cylindrical, and do they flatten out something?
Yeah, that is a really great question. I don't know. I haven't looked at high redshift yet, but we have all the data. I just haven't gotten around to it yet. I would expect that to be the case.
Okay, let's thank Cassi again.
Okay, great. Oh. All right. Can everyone hear me all right? Yes? Good. Okay, great. So, hey everyone, my name is Mike Foley. I'm a 6th year grad student now working with Alyssa Goodman and Lars Hernquist. And being in my 6th year, I've kind of accepted that I'm officially an elder grad student now, which is kind of painful to admit. My back is also painful. But it's, as an elder grad student, I really want to highlight some of the work that's been done by people who have just joined us in our CFA community or will hopefully join us very soon. So if you see a face and a name in any of these slides, it means they're working with us at the CFA community, so I highly encourage you to reach out. But today I wanted to talk to you about shock turbulence interactions in star formation. And I just am starting off with a very sort of picturesque view of the Orion constellation. But what I'm also highlighting in those colored points are 3 molecular clouds projected onto the sky. Orion A in green, Orion B in blue, and Orion Lambda in purple. And then this big purple sphere is actually a giant shell that falls right in front of all 3 of these clouds that we've been able to constrain in 3D, and it sort of sets the stage for what I want to talk about in the rest of the talk. So thanks to 3D dust mapping techniques, we've actually been able to discover that those 3 clouds that I just showed that fall right in the center of the constellation actually lie on the surface of a big shell of dust that we're calling the Orion shell. And using a variety of 3D and 2D observables, we've been able to sort of map out what we think the history of this shell formation and evolution is. Over the last few mega years, we think 1 to 2 supernovae at least contributed to the formation of this shell and possibly the formation of those molecular clouds. So with just sort of one example of this, it's kind of interesting that you have molecular clouds fall on the surface of a shell that seems to be produced by stellar feedback processes like stellar winds and supernovae. But it turns out that through our entire sort of local patch of the ISM, we've been able to map out a lot more shells, including the local bubble in which we reside. And so what I'm showing here is a collection of structures that have all been mapped out using 3D dust mapping techniques and constrained using other observables. So the sun is right at the center, very much not to scale, but that's the location. And in red, that long straight line is called the Radcliffe wave, because if you look at it in 3D, it actually appears to oscillate. And that, we believe, is the local arm of the Milky Way. And you might see a number of other spherical-looking structures in this vicinity. These are all shells that have been mapped out using 3D dust mapping. So at least around our sun, we have sort of a very bubbly environment. And it turns out that most of the famous star-forming regions in our local ISM, shown in white here, fall on the surfaces of these shells. So it suggests that, at least in our local patch of the galaxy, a lot of the star formation we observe is triggered by these feedback events. So as shells sweep up material in the local ISM, eventually it becomes dense enough to start collapsing and forming molecular clouds that in turn form stars. And so I just wanted to highlight 3 people who have recently joined us at the CFA. So Theo O'Neill is a new graduate student. They've done incredible work on the local bubble. Ralph Konietzka is also a new grad student. They've done incredible work on the Radcliffe wave. And Catherine Zucker has done everything and everything. They were with us as a grad student, but they've just joined us as a permanent staff scientist. And so if you're interested in any of these topics, I highly encourage you to talk to any of these 3 incredible people, especially Catherine, who's looking for new students and collaborators. So we've looked a little bit at sort of our local patch of the ISM. How do we know that's actually representative? Well, we can go to observations of other galaxies. So one galaxy we've considered has been M33, where we have great observations of H1, H alpha, and CO. So what I'm showing here is a single really large bubble that we've identified in M33 in H1, but it has a really nice rim of H alpha, shown in red, and CO, which is a tracer of molecular gas, also appears along the edge of this bubble, shown in green here. So we've been able to identify a lot of very nice analogs to our sort of like local ISM situation in external galaxies. And Toby Sonnenberg, who is an undergraduate, he has made a wonderful catalog looking at some of the 100 most prominent bubbles in M33 and kind of studied their properties and how the molecular gas in those bubbles relates to their overall structure. And one of the cool things he found is that on the edges of these bubbles, there's an excess of CO emission in the direction of galactic rotation versus the opposite direction. And so that does suggest that there is sort of a preferential formation pathway for molecular gas on one side of these bubbles that we're still kind of investigating kind of what that means. But it was an interesting finding. And to further elucidate the physics, we think going to simulations might help. So what we've been using have been Sarah Jefferson simulations, which have great constraints on the molecular gas formation and evolution in a galaxy and a really nice feedback model. And this work has been led by Aaron Angris, who's a fantastic undergraduate at Northeastern. He's applying for grad school this fall. So look out for his application. We'd be really lucky to have him as a grad student. But he has been looking at all the bubbles that form in this simulation and then tracking them over time to see how, first off, the bubbles just progress as more supernovae go off, other stellar feedback processes occur, but also to see how the molecular gas evolves along their surface. So this is still ongoing work, but we're really excited about the data set he's producing, and we should have some more answers soon. So his paper's in preparation. Look out for that in the next couple months. And this is just a pretty movie showing some of these bubbles evolving. What we really want to answer is like these large voids in the density of the gas, which ones are just produced by normal galactic shear, other sort of standard processes, and which ones are feedback driven, and how much feedback actually contributes to the formation of molecular gas on the edges of them. And so all of these bubbles forming molecular gas and whatnot reduce down to kind of a single problem, which is a shock moving into some ambient turbulent gas. And so I've been looking at sort of isolated simulations where we look at only that. We just have a single shock moving into some turbulent gas, and then we vary a bunch of different parameters to see how that changes. So the first paper is just changing the Mach number of the shock and the Mach number of the turbulence. So just looking at the hydrodynamics and seeing what we can extract from the dynamics of the gas. And so here what I'm showing is just density projections where the Mach number of the shock increases from left to right, so Mach 5, 10, and 15, and then the Mach number of the turbulence increases from bottom to top at 2, 5, and 10. You can see that like as the turbulence increases in strength, then you blow apart the shock very quickly, and as the shock increases in Mach number, you maintain a more coherent shock front. So a study like this lets us place constraints on sort of the lifetimes of shocks, as well as other things. And the beautiful thing is it's scale free. So you can scale it to whatever kind of physical scenario you would like. That could be in a molecular cloud, that could be in the CGM. You just adopt sort of a velocity and a length scale. And so what I want to show now is a little bit what we've been looking into, how these shocks drive compressive motions. So the motions that we think might set the seeds for star formation. And so this movie here is just making slices of these previous simulations, but going into the screen. So we're just stepping farther and farther into the screen here. And now I'm showing white as density. And you can see with this being the shock front, it's very corrugated, it's very warped. It's hard to identify sort of like a nice, strong structure. But we can look at the divergence of the velocity field and make some nice constraints on which things are compressing, which things are expanding. And so red here are things that are undergoing compressive motions, and blue are things that are undergoing more expansive motions. And if we take this and extrapolate to a scenario that we've seen kind of observationally, so maybe you have a bubble that's a radius of about 100 parsecs, has a shell width of about 20 parsecs, which we scale up this sort of shock region that's shown in red here, and take the amount of compressive motions that are happening in that shock region between those red lines, and use scalings for the CNM, we get a mass convergence in the shell of this hypothetical bubble of around 1 × 10⁴ solar masses per megayear, which is in the range of what we expect for producing just a molecular cloud for a bubble of these size. So in these simulations, we only have hydrodynamics so far. So the next step is turning on gravity, seeing what actually collapses and how we can extend it to our observational comparisons. But at least order of magnitude, we're driving sort of the motions we want to see. So to just wrap up, star formation in the solar neighborhood appears to be predominantly driven by stellar feedback processes. But we can go to extragalactic observations to try and put those observations that we have in the Milky Way in context. Then we can further go to simulations and try and track the evolution of these bubbles, see how they contribute to star formation over time. And fundamentally, if we go down to the problem of a shock moving into turbulence, that could provide further insights into what's actually going on in a galactic context. So, thanks.
One interesting question is whether the local bubble affects our life. We are now at the center of it.
Yeah.
But we came into the center over the past 10 million years or so, right? So we did not witness those supernovae, although they might have affected us. Can you comment on that?
So that's a great question. So the sun did in fact move from outside the local bubble into it, and we think it crossed over the shell about 5 million years ago. We can go to the geological record on Earth at about 5 million years ago, and there's an enhancement in iron 60, which is produced in supernovae. So we can actually start looking at the geological record on Earth and constraining some of the nearby supernova timing. And so Catherine has also been doing some amazing studies about that. So if you're interested, I highly recommend talking with her more.
Thank you. Up there,
I'm
there was a
here,
question.
sorry.
Hello.
So that was Catherine, right?
Oh, yeah, and
You cannot see it.
there's actually a paper, Avi, that you're
I
actually.
know. This question was not innocent. Any other comments, questions? Yes, please.
So, isn't there another dimensionless scale which is like the size of the largest eddies driving the turbulence to something about the size of the shock?
Yeah.
So like you were talking about these ratios of velocities. How does that fit in and like what are those scales in this?
No, that's a great
As
question.
you try to like scale this to different situations.
Yeah. So for our purposes, we've just kind of been agnostic on like what is driving the turbulence, but what could be driving that turbulence on these larger scales might be these sort of feedback processes.
Yeah, exactly.
And so we've remained a little bit agnostic to that. We just say that there is turbulence, and we drive at sort of like decently large scales, but we're not including any sort of realistic connection between some of these feedback processes, other galactic processes, and the turbulence.
So the largest like overturns are then kind of like the size of the bubble, sort of thing.
Exactly, yeah.
Yes,
So that's a great
go
thing.
ahead.
So what are your assumptions about the cooling in these shots?
So that's a great, in the simulations at least, we haven't included heating and cooling yet, but that'll make a huge impact for seeing which regions can actually collapse and cool. In the shells of the bubble, it appears that most of the cold molecular gas is kind of comfortable relying in the shells. So we think that the cooling is happening effectively, kind of across a variety of scales. There are even some sort of like smaller clumps that are found within these bubbles that do appear to be relatively kind of cool and dense. So in terms of putting it into the simulations at the shock turbulence side, that's still a huge question and something to consider more. Yeah.
Yes.
Do you think there could be a way to simulate the systems you're working with physically, to actually physically manifest these bubbles? Is that something you've come across?
Yeah. So I would say our best method for doing that right now is using a galactic scale simulation, sort of like with
I don't mean simulation. I mean like in some kind of physical, tangible system.
Like in
a gas or quantum gas or some kind of physical simulation of this mechanism as a way to better understand it.
That would be sweet. I have no idea how to do that, but that would be, if anyone has ideas, I'd love to talk. But yeah, that would be very cool. I'm not sure immediately how to.
So Mike, it looks like this collaboration is so large that when you submit papers, is there anyone left to referee? Or
Very few, very few. That's the strategy, though.
Let's thank Mike again.
Okay, so I'm going to introduce an entropy stability for the fragmentation of turbulent clouds, some work I did with George Field, and seems to have been published a long time ago, but if you were on the planet Earth for the last couple of years, you remember our timescales were very much disrupted. So I'm just going to jump into it, and I'll get to the context later. So to start off with, the general idea is that let's think about stars. They have a negative heat capacity, so they lose energy through radiation. They contract, causes an increase in gravitational potential energy. The thermal velocities keep up with that, and the temperature increases with the loss of energy, and that's the negative heat capacity. So that's a general property of self-gravitating systems. So if we think about a molecular cloud, imagine that there's a small perturbation, so it has a smaller radius and a larger turbulent velocity, and it's losing energy at some turbulent dissipation rate, which we say is a factor gamma times the crossing time, and therefore the perturbation is losing energy faster than the cloud. So another way to think of it is to say that the perturbation has to be supported by smaller wavelength turbulence modes, which have a shorter lifetime than the longer wavelength modes. So the change in the turbulent kinetic energy is then a function of both the change in the radius, so the turbulent energy is going up, and the change and the loss of turbulent energy due to turbulent dissipation. So what I want to do is develop a dispersion relation for the growth rate of this perturbation. So we have the rate of energy transfer, gamma times the crossing time. We use the time-dependent form of the virial equation to capture this self-gravitating property, which gives us the negative heat capacity. And then we have standard exponentially growing perturbations, which we analyze in the linear mode, and the growth rate is n. So since this is a cooling instability, we expect that there's an entropy function which is monotonic with the evolution. So it's a little easier to keep track of than, say, sigma, which can increase or decrease. So how do we define an entropy? So we start with the first law of thermodynamics, which is up here. Take our definitions from the virial average systems, that's the energy per unit mass and the pressure. You plug those in there, and then you come up with a result like that, and compare that to the second law, and then you can see that this quantity log sigma r is analogous to the thermodynamic entropy. Right. So that's what we say is the definition of the entropy in the turbulent system. And you say, well, that looks a little bit odd. Who ever heard of entropy as being sigma r? So you can think about it this way. So Boltzmann's entropy is the log of the number of microstates. And the number of microstates is sort of generically the energy to the 3/2 power times the volume, which then with our definitions gives you sigma cubed r cubed. And so you come back to that same form for the turbulent entropy, right? So we non-dimensionalize the equations, and then we're going to use for the entropy this quantity W, which is within a nonlinear scaling equivalent to this turbulent entropy. And so with S being the turbulent velocity, you see that this is the kinetic energy here divided by the time scale, which is just gamma in non-dimensional units. The time-dependent virial average, so that's this term you normally cross out when you're thinking about virial equilibrium. So again, that's the kinetic energy and the potential energy. I'll go back one, forgot to say. So then we put in the perturbations. You have a first-order differential equation, a second-order differential equation, and then that means that the equation for the growth rate is a cubic equation. So that has 3 roots. That has one real root, which gives you the growth rate, and 2 imaginary roots, which are complex conjugates down here. So those represent oscillations on the gravitational time scale. So what this says is that as a function of the dissipation time scale, the perturbations grow faster for a shorter dissipation or a cooling time. So now with those 2 differential equations that I had before, I can solve for the evolution of the cloud as a function of time, just convert them to a system of coupled first-order equations. And then I can study the fragmentation. So I need a definition of fragmentation. So let's just pick the Jeans mass and Spitzer's definition. And then we say that, so the Jeans mass is changing as a function of time because it depends on the turbulent velocity and the average density. And when the Jeans mass becomes small enough that there are 2 Jeans masses for the fixed mass of the cloud, let's say, suppose that the cloud can fragment into 2. All right. So the mass over the Jeans mass is the number of fragments. All right, so here's the evolution. So if I say that the turbulent dissipation time then is gamma of 1/2, so it's half a crossing time, so that's quite fast. Then the cloud will start here at non-dimensional units at 1 and evolve up to 2 within a quarter crossing time, right? On the other hand, if gamma is 2, then the cloud never fragments, right? So you can see these oscillations on the gravitational time scale, and the cloud becomes smaller and smaller, and the time scale for the oscillations becomes shorter. And what's happening there is that if the turbulent dissipation time scale, cooling, is very long, then the cloud just can become virialized and erase the perturbations before they have a chance to grow. And then, of course, there is a critical value for the dissipation rate of 0.7, but it's not a terribly significant number owing to the approximations in deriving this result. It's just that it exists and it's of order unity. All right, so then I say, well, what can I do in terms of looking for evidence for this in the observations? So I picked the Boston University 5-College Radio Observatory Galactic Ring Survey in 13CO. So the galactic ring is a collection of molecular clouds about 5 kiloparsecs from the galactic center. It has most of the molecular mass in the galaxy, And like everything else in astronomy, it's not named properly because it really isn't a ring, but it's a bunch of overlapping spiral arms. Okay. So here's the spectrum in 13CO of the center of that cloud. And so this is kilometers per second, and the units are brightness in terms of Kelvin, which is the only only unit in radio astronomy that has a standard definition in physics. Otherwise, radio astronomers like units like that, Kelvin, kilometers, parsec squared. So what's that? So you take this unit, which is brightness, so that's, what is it, watts per meter squared per hertz per steradian, right? Then you multiply by the bandwidth, that's kilometers per second. Then you multiply by the steradians and convert it to parsecs at the distance of the source. And the significance of that is that in that unit, this map of 13CO is directly proportional to the column density of 13CO. And then with some assumption on astrochemistry, directly proportional to the molecular hydrogen density, column density. So you can think of that as a map of the column density in grams per centimeter cubed, squared, sorry. All right, and so not all the clouds look like that. Some of them are more complicated, and they show more evidence of fragmentation. But nonetheless, so what I do here is I take my cloud, I pick this peak here, and then I do an azimuthal average around the cloud. So I'm in grams per centimeter squared, and I do my azimuthal average. I extract my spherical cow to match the spherical assumptions in the equations, and then I can come up with a radial density profile, right? And then I non-dimensionalize them so I got 600 clouds so far. So the full width half max is always 1, and the peak column density is 1. All right, so I average them all together and compare that to a hydrostatic profile, right? And it's a very good match. Now, it doesn't mean that the cloud is hydrostatic. It means that it's virialized sort of well enough that a function of radius, the gravitational and potential energies kind of balance. So what state is the cloud in then, right? So I can plot them on this figure here, and it says, so this is the virial equation. So if I leave off the external pressure, this is just the kinetic energy and the potential energy divided by R. So I plot all the clouds here, and this line is the line of virial equilibrium with no pressure, right? So all the clouds are kind of clustered over here to the left, and what these lines are different external pressures from 10 to the 3 to 10 to the, 6 Kelvin per centimeter cubed. What's that external pressure? Well, it's the weight of the surrounding molecular gas, right? It's all this stuff. Right? So you cut the cloud at some radius, and you've got all that weight. And this large variation in the external pressure is just owing to the mathematical simplicity that I forced onto this complex turbulent structure. Right? So now I say all the clouds are on this line of critical stability. So you say, well, what's that? So if you are familiar with the Bonner-Ebert theory, which same applies to clouds in virial equilibrium, I can just plot in hydrostatic equilibrium pressure versus radius or volume, and I have a curve like this. So if you're on this side of the curve, I take the cloud and it's confined by an external pressure, and I squeeze it, and it goes up here, and then I let the pressure off and it goes back. And then I keep squeezing it, right? And it gets right up to the top, and you squeeze it a little bit more, and then all of a sudden gravity takes over, and you go, wait, take the pressure off. And I say, no, it's too late. It goes into gravitational collapse. So that's the line of critical stability. So what this says so far is that the observations suggest that the conditions are consistent with those that would allow this cooling instability to operate, right? And then at critical stability, it's not necessarily that the cloud goes into gravitational collapse, but it could fragment or it could collapse depending on the ratio of the dissipation and dynamical timescales. So now, right, there is this theory of graviturbulent star formation, which is compression between turbulent eddies. So the idea is that you have turbulence, eddies collide, the local density exceeds the gene's density, it goes into star formation. But that theory cannot explain any of these observations. Then when we think about turbulence, we normally think about a Kolmogorov cascade where the turbulence is driven on the outer scale and dissipated on the smaller scale. But in this cooling instability, the turbulence is generated on all scales by the conversion of potential to kinetic energy. So in that sense, it's similar to this theory in 1953 that Hoyle proposed for fragmentation based on the gravitational timescale. Right? And Hoyle called his, this turbulence, this hierarchy, he called it gravitational turbulence. So that's, time is up, so there we are.
So Eric, it would be interesting to check what the implications are for the mass function of stars, because obviously
yeah. Well, I know a little bit about that so far. So let's see if I can answer this very quickly. Right. So here's the Taurus star forming region, right? And there it's 600 cores in here, and there are no stars in the Taurus region that are greater than 2 solar masses. So in effect, it doesn't have a mass function. Right? Now, what we suppose is happening here is that, right, so if you have a rapid dissipation time scale, then the cloud is sort of cools off and it just chills rapidly, and all these little fragments get frozen in place, right? That's this here. And the turbulent velocity is decreasing as this happens, right? Now, this is in non-dimensional units, not just whatever you start with, not sound speed. Right? But this process continues on a hierarchy until you come down to the sound speed. So the turbulence equals the sound speed. Then at that point, you end up in this kind of regime where the turbulent dissipation time is very long because you're dealing with subsonic turbulence. So these clouds will no longer fragment. And that's why they're sitting there for 1 million years, slowly contracting and forming individual stars, or possibly a binary through some other process, disk instability or something like that. So you can, at least in concept, come up with a understanding of why these low mass star forming regions have a different IMF than the high mass star forming regions. Now, to produce an IMF, which is kind of like a log normal, you know, this is child's play, right? Anybody can do that. Any theory will give you a log normal. So that's no constraint at all, but it can be done.
Okay, it sounds like the multiverse. Anything is possible. Question? Go ahead, Eva.
Thanks. Yeah, it seems like this analysis is fairly dependent on sort of a time-dependent virial equation being satisfied, right? Is there a time, like a short enough time scale on which that breaks down?
Yeah, right. So, right, that's what I had on one view graph. You know, so the cloud has to be sort of virialized enough that it has this self-gravitating property, so it has a negative heat capacity overall. Right? So I think that's the relevant timescale that you're referring to. And then there's this other timescale, which is the cooling timescale, right, which is on the order of the crossing time for turbulence. But you know, within a factor of order unity, you get differences in behavior. So.
Okay, we need to move on, so let's thank Eric.
All right. Hello, my name is Misha Rashkovetsky. I'm a fourth year grad student here. Today I'm going to talk about my work on semi-analytical covariance matrices for DESI galaxies two-point correlation function and its application to DESI early BAO results. This talk is mainly based on those two papers. Before starting the presentation, I would like to thank the DESI sponsors and the 69 participating institutions. I'd like to begin by discussing the two-point correlation function, which describes the excess probability of finding two galaxies separated by a certain distance. In our context, compared to the random scatter case. It can be estimated by counting pairs of galaxies, as shown in the animation on the right. It is simplified because one has to do this 3 times for pairs between data galaxies denoted by D and random points denoted by R, representing the background density and surveyed geometry, and divide as shown in this equation. One of the key goals of DESI is measuring clustering like this. Baryon acoustic oscillations, or BAO, is a prominent feature in the correlation function scaled by separation squared. The scale of the BAO peak is related to the cosmological distances and ultimately to the rate of the expansion of the universe. Knowing that, we can answer big questions like try to answer big questions like the nature of the dark energy, Hubble tension, test gravity on the larger scales, and so on. Now, errors and their correlations are crucial for interpretation of physical data. One can estimate them rather simply by repeating measurements and estimating the scatter in them, but we only have one universe and one DESI survey, so we must rely on suites of simulated or mock catalogs. The relative precision of the covariance matrix is then determined by the number of repetitions. And each simulation needs to be representative of real data and be accurate, which leads to 2 problems. One, even one very precise simulation is very expensive, so we need some compromise between quality and quantity. Second, the computation cost for the covariance matrix is still very high, and it's hard to recalibrate the mocks and reprocess everything if something changes. And this problem becomes even harder for high-density tracers like DESI bright galaxies. But for the computation of the covariance, we are basically considering all the pairs of pairs configurations, which leads to a 4-point configuration and therefore 4-point function. Some of the points may coincide, leading to 3- and 2-point configurations. We separate these different contributions to the full covariance matrix. We use shot noise approximation here to handle the coinciding points and the square of the overdensity appearing there. And as a result, the different terms are scaled differently with number density as shown here. And we also use Wick's theorem to express part of the 4-point function through 2-point functions. These ideas are the foundation of the Rascal-C code, which computes the covariance matrix integrals with importance sampling. It requires a random catalog to sample from, which will account for survey geometry, boundaries and selection, and so on. And the 2-point correlation function, which can be a direct measurement or a model. We drop currently the non-Gaussian correlation functions because they are hard to measure or model consistently. Instead, we rescale the remaining Gaussian terms through density increase or through density decrease or equivalent to shot noise increase. Remember the different scalings from previous slide. This gives us more correlations on small scales, which is pretty much like what we expect from non-Gaussianity. There is only one parameter involved that can be tuned with jackknife covariance, which is itself like the scatter between different parts of data. It has certain caveats, so it's predicted separately for this part. Or alternatively, this one parameter can be tuned on sample covariance with a smaller number of mocks. And that's where semi-analytical comes into play, not fully analytical. The code is fast, flexible, smooth, and precise. And to prove the last statement, I just want to show this comparison of error bars projected from different covariance matrices for our main parameter of interest, the scale of the BAO, before and after reconstruction, which is a procedure to enhance the signal. Note the narrow ranges in the plot. The blue square is sample covariance with 2.2% error bars, and the remaining points are Rascal-C results. The orange triangle pointing downwards is a low noise mock clustering with no shot noise rescaling. The red triangle pointing upwards is pretty much the same, but with rescaling to fit the mock sample covariance, and the green dots are the runs with realistic amount of noise in the mock clustering, and also rescaled with the jackknife covariance. You can see there is a great agreement before reconstruction, also quite good agreement after reconstruction, and the shot noise rescaling does help noticeably. Also, I want to mention a significant part of the paper dedicated to the more general problem of comparison of covariance matrices, which is a complex problem. First, it is not trivial to set the desired precision and weigh it against the computation cost. Second, our reference is mock sample covariance in this case, which is noisy and imperfect for reasons I mentioned before. Moreover, the covariance matrix is a high-dimensional object, so it's not clear which parts are important. To illustrate this, I show some plots that some people make comparing correlation matrices in the top and square roots of the diagonals, the error bars in the bottom. The upper plot is rather unclear, while the lower seems to suggest the difference is quite significant, while actually the BAO scale error bars here agree pretty well. One can get away with comparing only a few parameters, but even then it's kind of hard to form a summary. We performed a generic analysis for samples following a normal distribution, which could be useful for you in other contexts. We use compact metrics, which have expectation values shifted from perfect due to noise, which is important, and also they have error bars themselves that can and should be understood. And now I'm going to switch to an application to the first detection of the BAO signal from early DESI galaxies data. First, let me give a brief description of the data we used. It was collected during just the first 2 months of DESI main survey operations. That's the other name, DESI-M2. We focus on 2 samples, luminous red galaxies LRG and bright galaxy sample BGS with an absolute red filter magnitude cut. In the bottom left, you can see a redshift distribution. On the right, sky footprints color-coded by completeness. And we have hundreds of thousands of galaxies, which are the same number as in some previous complete surveys. Now, you might ask, why not just go with mock covariance as before? There were certain problems. For LRG, the mocks were calibrated on an earlier clustering measurement, namely from survey validation data. And with the updated measurement, there were significant differences around 20 megaparsec over H here, which are important for covariance metrics at pretty much all scales. and it's an expensive affair to repeat all this calibration. For BGS, due to much higher number density, the mocks were available with even lower realism. So it was a great opportunity to use Rascal C. Here are the results for luminous red galaxies. The left panel shows measurements and the best fit model, while on the right it's a detection significance plot. We have 5 sigma detection and 1.6% precision, which is comparable to both DR9 CMAS of 1.6 and 1% in DR12. For bright galaxy sample, we have 3 sigma detection and 2.6% precision, again comparable with both DR9 1.7%, which is a bit better, but still. To sum up, I hope I have convinced you that the covariance matrix estimation is a hard and interesting problem, and that Rascal C approach is useful. Now, only 2 months of DESI are comparable to SDSS3, which ran for 6 years for BAO precision. And the future DESI error bars will be amazing, and we have many tracers. The cosmological analysis will be presented with year 1, hopefully by the middle of next year. And here I show just how much the LRG coverage improves between the data that has been analyzed to full year 1. Thank you for your attention. I will be happy to take questions.
So Misha, in principle, if you have a 4-point function, you can check it for Gaussianity, right? Because it should be the square of the 2-point function for a Gaussian field. So would you expect, would you constrain non-Gaussianity to a significant level or not much?
Well, I wouldn't say I can. On the scale that matters, the non-Gaussianity isn't that strong, so it's pretty hard to constrain. The short noise rescalings in question are pretty close to 1, no more than 1.1 typically.
Ramesh?
Yes, you got these 2 samples, LRG and the BGS, right?
Yes.
And they seem to be different redshift ranges.
Yeah, right.
So is that the real reason for doing the 2 samples, just to explore different redshifts, or do you expect other differences between the 2?
Well, they do have different selection strategies and so on. I'm not a very big expert on that though. But yeah, one of the ideas is to explore different redshift ranges. But yeah, in principle, in year 1, we are going to do 3 LRG redshift bins, and for BGS, maybe 2. So far, we are still doing only 1 redshift range for BGS.
Any other comments, questions? If not, let's thank all our speakers today.